Good morning, everybody. So today I will be solving this problem. So it's a problem 25 from Holiday and Resnick in chapter 29. So chapter magnetic field. And this is the image of a mass spectrometer. So let's see the image and follow the text. So a mass spectrometer is used to separate uranium ions of mass. So here we have a mass of the ion. Let's call it small m. And charge of one ion. So charge, let's call it small q. All right. These ions are accelerated through potential difference. So maybe they are produced here and they are accelerated through potential difference. So that's V, and V is equal to what? 100 kilovolt. So V is equal to what? 100 kilovolt. And then pass into uniform magnetic field. So here it shows us a region of magnetic field here. So they are accelerated. So here the ions, they will have a certain speed. All right, same ion, positively charged. So, and here they will bend in a circular path of radius 1 meter. So we have the radius here, r is 1 meter, after traveling through 180 degree. So of course they will travel here along a half circle, so that's 180 degree path. That's what it means. There is an opening here and they go through column. They go through slit of width 1 millimeter and height 1 centimeter, whatever. So they go through here and they get collected in a cup. So here we have a cup, okay? And the ions, they get collected. And here we have several questions. So I will start one question at a time. So I will remove all the other questions. So you start with question A. What is the magnitude of the magnetic field, the perpendicular magnetic field in the separator? Well, they ask us what is the magnetic field in this region, basically. It's exactly similar to the sample problem that we have seen in lecture. And to solve it, I will repeat the steps here. We start with, we have a radius, magnetic field. So we have what is the radius of this circular path. We have a formula in class. If you want, you can just derive it. The force, the magnetic force is equal to centripetal force. Centripetal force, mv squared over r. From this you deduce qb equal mv over r. And from here I can get B. I'm looking for B now, for magnetic field. So I can get B equal mv over qr. Fine. So I know the mass of ion, I know the charge of ion, I know the radius, I don't know the speed. So for the speed, we use conservation of energy. Here, the ions are accelerated through potential, so they have a potential energy here. So we apply conservation of energy. And we have the potential energy, the electrical one, is equal to what? To the kinetic energy. So basically the ions start from rest here and they get accelerated, and here they will have a certain kinetic energy. So half mv squared. So I can calculate V from here, put it here and get B. Or instead I can combine the two formula. So if you combine the two formula, I leave this for you, you will find that if you combine 1 and 2, so combining 1 and 2, we get B equal square root of 2m the potential over q r squared. Or you can just You have Q, you have V, you have the mass. You can just calculate V and plug it here and get B. So it's not required to get this formula. So if you do the numerical application, you get B equal 0.495 Tesla. Well, we can round it to 0.5 Tesla. That's almost half Tesla. Okay, so that's the solution for question A. So the second part is state that if the machine is used to separate out 100 milligram of material, so we don't separate just one ion, we separate a lot of ions. So the quantity of these ions are, the mass of these ions, the weight, is 100 milligram per hour. Okay, so each hour we separate 100 milligram of uranium ions. The currents, so what is calculated? The current of the desired ion in the machine. Okay, the current. Well, here it seems a little bit surprising because we learned electrical current. We learned more electrical current. What is electrical current? That's the charge of basically what? Electrons that circulate through wire during a certain number of time. That's fine. So here he don't say electrical current, he say the current. The current of what? Of ions. The current of ions. There is a charge changing with time, so that's what we call current. Okay? So basically, it will not surprise anyone, I believe, if I say that the current, well, is equal to the charge per time. Okay? So the charge of ions, of all ions, in 1 hour. Is that fine? Does that make sense? The charge of all ions that are separated, that are collected in a cup during 1 hour. All right, so that's the current. I define current like this, that's charge over time. Fine. So I know, so all what I need to know, what is this? What is the charge of all ions? So basically, that's not quite difficult. We have an information here. We have the total mass of all ions. Okay. So I can write simply, there is a lot of way how to do it. I can write simply that the charge of all ions, the total charge during 1 hour, what is it? That's the charge of one ion times the number of ions. How many ions are there? So again, the total charge collected during 1 hour, Q, that's the charge of one ion times the number of ions that are separated during 1 hour. So how I can know this number now? So I have the mass, the total mass, and I know the mass of one ion. I have the total mass of all ions, and I know the mass of one ion. So n ion, the number of ion, what is it? Simple. That's the total mass per the mass of one ion. You do that. You plug in the number, 100 milligram. Don't forget that's milligram. What is milligram? That's 10 to power minus 6 kilogram. That's standard unit. It's kilogram. Okay, there is no more conversion. Charge in coulomb, the mass in the mass of ion, one ion is in kilogram, so everything is fine. If you do that, you will find the charge equal to what? 81.6 coulomb. So there is 81.6 coulomb of charge during 1 hour. Well, now it's trivial. What is the current? That's the charge per time. So that's 81.6 coulomb per 1 hour, that's 3,600 seconds. And this gives me 0.0227 ampere. So let's go to question C now. The question is, what is the thermal energy? The thermal energy produced in the cup during 1 hour. Just remind you here the result of question B. the charge of the total charge of uranium ions, the total charge during 1 hour, is 81.6 coulomb. So let's think about what is this thermal energy. Let's do an energy balance, actually. Okay, we know that energy is conserved. So let's use this principle of conservation of energy. Let's see. Let me take one ion, just one ion, and see how the energy related to this one ion change. So the ion will go from here to here. Well, what is the energy here? Q times V, potential energy. When he go in magnetic field region, at this point, what is the energy? Half mv squared. Go through a region of B field. Does this energy change? No. Why is that? The speed do not change in a magnetic field region. So the ion will arrive here with half mv squared and will come to the cap with half mv squared. That's an energy that entered the cap, and that's the energy that is converted into thermal energy. So for one ion, the thermal energy in the cap, produced in the cap, that's half mv squared, that's the kinetic energy of this ion, and that's equal to qv. That's the potential energy from beginning. Let me say it in a different way. That's the initial, that's the final. There is no dissipation here. There's nothing that dissipates energy. So the initial energy is equal to the final energy. What is the initial energy? That's the potential energy, electrical potential energy, QV. What is the final energy? It says here, that's the thermal energy in the cap. Okay, so this is principle of conservation of energy, and I can write for one ions we have QV equal half mv squared, just to, and equal to the thermal energy for one ion. Now for all ions during 1 hour, well, what we have, what is the thermal energy? What is the thermal energy? I can write it like this. That's the total kinetic energy of all ions. You add them up. That's the total potential energy of all ions. You add them up. So that's the number of ions times QV. But what is the number of ions times Q? That's the total charge times V. So a simple balance of energy gives us the result. So now the thermal energy, what is it? 81.6 coulomb times the voltage, 100 kilovolt, so kilovolt 10 to power 3 volt, and this give you 8.16 10 to power 6 joule. Okay, so that's the answer of this problem, and see you in my next video.